Thermal design power, or TDP, is a term used by AMD and Intel to refer in an extremely broad sense to the rate at which a CPU cooler must dissipate heat from the chip to allow it to perform as advertised. Sort of. Depending on the specific formula and the product, this number often ends up a combination of sciencey variables and voodoo mysticism, ultimately culminating in a figure that's used to beat down forum users over which processor has a lower advertised TDP. With the push of Ryzen 3000, we're focusing today on how AMD defines TDP and what its formula actually breaks into, and how that differs from the way cooler manufacturers define it. Buying a 95-watt TDP processor and a 95-watt TDP CPU cooler doesn't mean that they're perfectly matched, and TDP is a much looser calculation than most would expect. There's also contention between cooler manufacturers and CPU manufacturers over how this should be accurately calculated versus calculated for marketing, something we'll explore in today's content. Before that, this video is brought to you by Thermal Grizzly's Conductonaut liquid metal. Conductonaut is what we've used in all of our liquid metal and delid thermal tests, capable of dropping CPU thermals significantly when replacing the stock thermal interface. Lower CPU thermals don't just allow better overclocks, but also lower noise levels because the transfer efficiency is increased. The mix of gallium and indium makes for a thermal conductivity of 73 watts per meter Kelvin, outclassing traditional pastes significantly. Learn more at the link in the description below. TDP is more of a number that's chosen by the CPU manufacturers, or at least in today's discussion, AMD, than it is calculated. The calculation is secondary, and it's secondary to choosing the number first because of the way the formula works. So ultimately, TDP is picked for a few reasons. Arguably, the internal reason that AMD or Intel might pick it does definitely have to do partly with marketing. And then there's also some compliance in working with the cooler manufacturers, working with people who design heat sinks and things like that. But a lot of this does have to do with marketing. Not all of it, but enough to talk about separately. If you don't believe us and are about to paste the formula for TDP in the comments, stick around for the video because we'll explain why this isn't as firm of a number as one might expect, especially when there's something like watts stuck at the end of it, which would seem pretty straightforward, but it's really not. This includes a little bit of math, but not much, and mostly just working through the formula so that everyone can understand what is TDP comprised of. What does it actually mean to have a 105-watt TDP? And some cooler manufacturers will stick a TDP number on a box. So then the question there is, if it's 105-watt TDP and the cooler says 105-watt, or maybe even 115, does that mean you are perfectly matched or even that you have slight overhead? So we're going to go through that today, along with breaking down the more marketing side of the TDP formula. TDP has been a pretty heavily mocked number by a subset of the enthusiast user base, both from Intel and AMD, but it's also frequently leaned upon in the world's most important discussions. Reddit arguments, where one's goal is only to insert intelligence over the next user. TDP is confusing in part because it's assigned a watt unit of measurement, but doesn't actually correlate to real electrical power consumption in the formulas that we're looking at today. Intel i7 CPUs, for instance, can sustain a 90 to 95 watt power consumption under full stock conditions, but only after the turbo boost duration is expired and if MCE is off. Otherwise, it'll burst higher, and then it comes down when the turbo duration limit dictates that it can come back down. So this is really part of the source of the confusion. You have a number assigned a unit of measurement called watts, but not once in the derivation of that number in AMD's formula for Ryzen 3000 or 1000 or whatever does a unit of power get calculated. AMD doesn't even have electrical power anywhere in its formula to define TDP, but people still use TDP figures to talk about how much power a CPU consumes. AMD itself uses this figure in press events to knock Intel subtly, even though the two companies have different backwards ways of reverse creating the TDP values that they want. TDP ends up being useless for just about anything that the end user might want to do or use it for. This requires some more discussion to better explain, and our goal today is to answer a few core questions. The core questions are straightforward. 1, how is TDP calculated and what is it? And we have the formula for how it's calculated, but the numbers are not, there's not really any fixed numbers in that formula, which makes it very interesting because you can kind of plug anything into it to get what you want. 2, can you use TDP to determine cooler choice? And if not, what's the next best means of choosing a cooler? And 3, does TDP correlate at all with electrical power consumption into the chip? That's what we're looking at. For the last point, we'll talk about how power consumption of, for example, an R9 3900X might equal 120 watts core and maybe 20-something watts, 24, 25 watts uncore, workload running over 140 watts in that condition for a 24-thread scenario, but how its TDP is listed as 105 watts, about a 40-watt difference potentially, maybe 35. So we'll look into whether that TDP value means anything. AMD's definition of TDP will be dissected over the entirety of this piece, but we'll start with the formula. And the formula is TDP watts equals T case degrees Celsius minus T ambient degrees Celsius divided by heatsink fan or HSF theta CA. Critically, and more on this later, we should note that each of these values changes based on the processor, or can change. So there's no fixed set of values, and each remains a variable for all processors. This means that TDP can be configured to equal other desirable numbers just by arbitrarily redefining values like T ambient or soft numbers like T case. These can be manipulated for the desired TDP value. We'll define each part of this more in a moment, but we should start with a table with some parameters that AMD uses for calculating each of its TDP values. A quick thanks to AMD for helping us fill out this chart with T case, T ambient, and HSF theta CA numbers, as well as answering some other questions that arose during the writing of this topic. The P0 numbers are not from AMD. They are through unofficial channels we sourced from internal AMD design guidance documents that we obtained with other sources, and they define P0 as, quote, the highest power, non-boosted P state for highest performance. And note that also T ambient changes for other processors like Threadripper parts, where STRX and SWRX Threadripper 3 parts have T ambient values in the TDP formula of 32C and 42C between processors groups A and B. So T ambient, although the same in that larger table we saw, will vary for other processors like those two Threadripper parts. Let's get back to the big table for the Ryzen 3000 desktop parts. We'll highlight the TDP column first. It doesn't take a genius to see that there's something strange here. The 3800X, the 3900X, the 3950X, all of them are 105 watt TDP parts, despite having different clocks, different core counts, different die arrangements, and greater thermal requirements on the higher end parts. The higher core count, higher frequency 3700X has the same 65 watt TDP as the 3600, not to mention that all of these numbers round cleanly to multiples of 5. We're going to break down AMD's explanation of TDP from the reviewer guide for the 3000 series Ryzen CPUs sentence by sentence, and then explain why this is all the case that it is. AMD's guide reads the following, quote, "It is a common mistake to conflate thermal watts, TDP, and electrical watts, power draw. Accurate knowledge of what TDP is and how to calculate it is therefore vitally important when drawing conclusions about the electrothermal characteristics of a silicon device." Now back to our words here and some of Wikipedia's. A watt is a watt. Wikipedia says that a watt is, quote, "a derived unit of 1 joule per second and is used to quantify the rate of energy transfer." In a Reddit post, AMD's Robert Halleck says, quote, "TDP is about thermal watts, not electrical watts. These are not the same." In a literal sense, that's not really true. Thermal and electrical watts are the same unit, in the same way that a cup of flour is the same as a cup of water, or a pound of bricks is the same as a pound of feathers.
I've got a question for you. What's heavier, a kilogram of steel or a kilogram of feathers? That's right, it's a kilogram of steel, because steel is heavier than feathers.
So the bigger thing here, though, moreover, is that the rate that a chip draws energy as electricity and releases energy as heat over a sufficient period of time to reach steady state will be functionally equivalent. They'll be roughly equal and will be the same over a sufficient amount of time. So no physical work is being done here, and there's no translation about any axis. There's no emission of energy as light, at least not yet. There's no RGB CPUs yet. And so heat will be nearly perfectly one-to-one out versus power in for a CPU scenario. And enough one-to-one where it doesn't matter to even argue any further than that. There is some conduction into the socket, into the pins, into the ILM, into the motherboard that doesn't need to be accounted for in the heat that's going through the IHS, but it's still heat. So the point stands there. It's just that that particular efficiency loss doesn't need to be calculated for in the heatsink calculation. Also, that's so small that it's irrelevant when compared to the heat that is going through the IHS. So here are the two most important factors to remember during any internet argument about TDP. That's really what we're here for, is so that you can use our content to attack other people on Reddit. Don't do that, that's terrible. Number one, once the system reaches steady state, the rate that heat is released in watts will be the same functionally as the electricity that is drawn in watts. That's point one. Point two, TDP is a man-made rule of thumb. It's not a precise measurement of thermal output, and we'll talk about that more later. And then AMD next says this, quote, thermal design power is strictly a measurement of the ASIC's thermal output, which defines the cooling solution necessary to achieve rated performance. From the confidential engineering documents that Gamers Nexus obtained, AMD's internal definition is this. TDP is the recommended design target power to use when designing a processor thermal solution. TDP is defined at a nominal voltage and maximum specified case or die temperature. TDP represents the sum of power consumed for all processor voltage rails. TDP as defined by the cooler manufacturers is different still from this, different from both AMD and from Intel. And we'll cover the cooler manufacturers' points of view in a few moments. We've gotten some comments from them, mostly off record. They tend to disagree, well, not even tend, they do disagree with both Intel and AMD with the CPU manufacturer's definition of TDP. So the cooler manufacturers are in a completely different mindset as the company that actually makes the thermal solution for those processors, which is interesting. The disagreements vary from casual to more vehement, depending on whom you ask and when. AMD's TDP does, quote, define the cooling solution necessary, but maybe not in a way that's helpful to the consumers who are browsing a web store for any of the major cooler manufacturer brands. And that's true for the most part of Intel as well, but that's a different topic than today. Maybe something we can explore later. Something that Ian Cutchess from Anatech has already done a great job on though. But today we're focusing on AMD. So AMD's reference to measuring an ASIC's thermal output also requires some explanation. An ASIC is an application-specific integrated circuit, referring to Ryzen CPUs in this context. CPUs, though, are general purpose, and therefore by definition, not ASICs, but that's a technicality. This explanation is an old one. It's been patched and edited a couple of times since Ryzen launched in 2017. The sentence in particular has become more loaded too than it was back then, because Precision Boost 2 means that performance of Ryzen 3000 chips scales strongly with temperature, and so, quote, rated performance is now a trickier prospect to quantify. As we showed, one of the best ways to overclock Ryzen is to drive its temperature sub-zero, for example, minus 80. And so this muddies the waters of what cooling solutions are really expected to achieve at a given TDP. Also, limited duration boosting means that no single number can effectively summarize thermal output for the AMD or Intel CPUs. TDP can't be strictly the measure of an ASIC's thermal output, in quotes there, because the thermal output changes based on workload and test length, among other things. AMD expands and says the following of its formula. Quote, the TDP formula is straightforward. TDP watts equals Tcase minus T ambient divided by heatsink fan theta Ca. Let's define all of these things finally. Tcase, as the first number we encounter, is externally defined as follows. Maximum temperature for the die heat spreader junction to achieve rated performance. AMD's internal definition from those engineering documents is this. Maximum case temperature. The maximum temperature when measured at the package location specified by the appropriate thermal design guide. Tcase max is used for thermal solution design and in thermal situations. And a lot of these definitions between internal and external are basically the same, but it does help to have some more detail. Tcase here means case, as in integrated heat spreader or IHS, not as in computer case. In a very strict sense, this refers to the temperature at the point where the silicon meets the IHS. Note that this isn't how hot does the CPU get, but how hot can the CPU get before Precision Boost 2 starts to throttle back. Lower Tcase would beget lower TDP in the formula. The next number in the formula is T ambient, which is the subtrahend deducted from the minuend Tcase before the result is divided by thermal resistance. AMD defines T ambient degrees Celsius as the, quote, maximum temperature at the heatsink fan inlet to achieve rated performance. Its internal definition, just for some elaboration here, is as follows. Local ambient temperature at processor heatsink inlet. This is not the external system ambient temperature. T ambient max is the maximum local ambient temperature supported by the theta dA. We think this is maybe die to ambient, but we're not sure. Theta dA value is stated in the thermal requirements section. If the ambient temperature exceeds T ambient max, then the thermal solution must be designed to a lower theta dA to maintain T die at max, that is at TDP. T ambient min specifies the minimum local ambient temperature, 5 degrees Celsius for Ryzen 3000, but obviously this is just a guideline. Systems operating in a lower ambient temperature are not supported, end quote. So HSF refers to the heatsink and fan, the CPU cooler, and then T ambient is the temperature of the air around the heatsink, whether it's an open bench or a PC case. Lower T ambient means higher TDP, but T ambient is defined by AMD in its TDP formula and is not defined by your own T ambient. AMD defines HSF theta CA, degrees Celsius over watts, as the, quote, minimum degrees Celsius per watt rating of the heatsink to achieve rated performance. Its internal definition for comparison says the minimum required heatsink resistance necessary to maintain the case temperature within specification for the thermal design power TDP and assumptions for the external ambient temperature and system temperature rise, TSYS. The heatsink fan is what stands between the CPU and the surrounding air, and theta CA is the thermal resistance between the CPU and the air. So theta CA, HSF theta CA is the thermal resistance of the heatsink. Lower is actually better here, not higher. So AMD's phrasing has some interpretive gray areas, to be kind to it. AMD's reviewer document should instead read maximum instead of minimum for that quote. So the quote should be the maximum degrees Celsius per watt rating of the heatsink, as lower is better, and so maximum would be the last value permissible for rated performance before becoming insufficient for rated performance. When we reached out, AMD clarified that, quote, you can interpret the original copy to mean the minimum standard, where lower values produce superior results. We're fighting over semantics, but you get the idea. So HSF theta CA is a direct measure of required heatsink quality, and from this guide, it appears to be how AMD rates its own coolers. Lower HSF theta CA means a higher TDP, and if we want to be less pompous in how we say it, it'd just be heatsink fan thermal resistance. So anyway, when you hear heatsink fan theta CA, that's all they really mean, is the thermal resistance measurement. And again, none of these numbers are constant nor concrete. They can change. And AMD changes the numbers based on which CPU it is. So for example, each variable is a value that has some interpretive dance and voodoo rituals that can be performed on it, aren't always, but they're involved for defining those nice round numbers that we get as the TDP values at the end of the formula. Let's revisit that formula again. We'll get it back on screen to remind everyone. All things defined, TDP in watts equals the difference between recommended maximum CPU temperature and recommended maximum ambient temperature divided by maximum recommended thermal resistance of a heatsink. TDP then is a result of plugging in the recommended room temperature, the CPU temperature, recommended case, and the cooler quality into a formula and then getting a somewhat firm number out of it, even though the variables that go into it can be freely defined and the data can be massaged to equate nearly any TDP value that you want, as you'll see further on. So AMD says this in its guide. Using the established TDP formula, we can compute an example in the form of the 105 watt AMD TM Ryzen 9 3900X. 61.8 minus 42 divided by 0.189 equals 104.76 TDP, with TKs as 61.8, optimal temperature for processor lid. The, quote, maximum temperature wording from the previous section has now been replaced by, quote, optimal temperature. As we've proven in past content with liquid nitrogen, stock settings, and frequency scale, which comically doesn't technically violate the warranty, even though PBO does without LN2, Ryzen 3000 frequencies keep scaling up with room temperature decreases even below 0 thanks to Precision Boost 2. And that's not the same as Precision Boost or overdrive, just to be clear. Saying 61.8C is an optimal temperature seems arbitrary, but this is the temperature that AMD claims the chip should be at or below to hit the frequency numbers on the box, though they still wouldn't until recently. Examples AMD has used in past iterations of this guide were 71.3 degrees Celsius for the 1300X, 60 degrees Celsius for the 1600X, and 56 degrees Celsius for the Threadripper 1600X. This was supposed to read 1950X. That was a typo by AMD. There's obviously no Threadripper 1600X. These numbers are complicated by AMD's policy of weird CPU temperature reporting on those older Ryzen chips too. There was a T-control value at the time, so you have T-control and T-die, and it's not 100% clear which one they're relying on in some of that old content. So we should get that chart of the values for the formula back on the screen from the beginning of this video. And we should also clarify that the TK's temperatures AMD lists in the chart at the start of the content and in this chart are not hard thresholds beyond which Precision Boost stops working. And likewise, they are not hard thresholds under which Precision Boost instantly hits maximum performance, the CRLN2 content. So instead, quote, the CPU will simply draw back on boost if TK is exceeded, as AMD says. We need to look back for a moment at the T ambient value. AMD says that for this example, 42 degrees Celsius T ambient is the optimal temperature for the case at heatsink fan inlet. Case T case, not computer case. Even if we trust that T case is based on chip specs, T ambient most certainly is not. Increasing T ambient makes TDP go down, and decreasing T ambient makes TDP go up. And AMD can freely choose T ambient. And examining again the older reviewer guides, optimal ambient is 32 degrees Celsius for the 1950X, 42 degrees Celsius for the 1300X, 42 degrees Celsius for the 1600X, and it's 42 degrees Celsius for every Ryzen 3000 chip release so far. We don't know about the 3950X presently. So this is a hot but realistic temperature for the case, internal case, computer case now, temperature, if you're working with sort of a poorly designed or poorly ventilated case, of which there are very many on the market, unfortunately. The next number is for thermal resistance. In its example, AMD chooses a HSF theta CA, or thermal resistance, and it then noted the following, quote, 0.189 theta CA is the objective AMD specification for cooler thermal performance to achieve the rated CPU performance. TDP is, according to AMD, a number that indicates required cooler quality. To calculate this number, you need HSF theta CA, which is, quote, the objective AMD specification for cooler performance, and this is a catch-22. From AMD's official Reddit explanation of TDP mentioned earlier, we learned the following, quote, TDP is a cooler spec to achieve what's printed on the box. From earlier in the same explanation, another quote, specifically, theta CA represents thermal resistance between the CPU heat spreader and the ambient environment. The lower the theta CA, the better the cooler is, end quote. Because the formula for TDP divides by theta CA, plugging in a better recommended cooler results in a higher TDP. So past versions of this explanation often include a line like, quote, the stock cooler for the example CPU corresponds with this specification. Our opinion is this. The AMD TDP formula takes three sort of useful numbers and blends them together into one unuseful number, at least for consumers. And that unuseful number can't be reverse engineered back into its original base values unless you are given most of those base values, basically all of them. And it's sort of like summarizing someone's personality by adding their birth date and the count of letters in their last name together. You don't get anything that means something at the end of it, but certainly you could draw comparisons between everyone's birth date plus last name characters to equal some value that can then be judged against each other for some version of superiority. So AMD did provide T-case, T-ambient, and HSF thermal resistance to us upon request. Those are not numbers that get printed on the box, and it's unlikely that most users will be exposed to those numbers unless they've now seen this content. So here's another helpful line from AMD's commentary. Quote, thermal conductivity of the processor die, heat spreader, HSF, and junction solder allow the AMD Ryzen processor to amortize the T-case implications of peak power values over time, allowing the CPU to automatically increase performance while remaining inside the thermal boundaries defined by the TDP. In our example processor, Precision Boost 2 will level off at 61.8 degrees T-case, degrees Celsius, or 142 watts peak PPT, whichever comes first. First off, amortize probably needs a definition more than the technical stuff. That means to pay off an obligation such as a mortgage gradually, usually by periodic payments of principal and interest or by payments to a sinking fund. You get the idea. But anyway, the other stuff, the technical stuff, PPT we talk about in our PBO content. If you'd like to learn more about that, that is one of the parameters that's important for PBO. But anyway, this quote is saying that in its base elements, there's a lot of metal on top of the CPU, and that acts as a thermal buffer. So even with spikes in power consumption, i.e. turbo, the thermals will be smoothed out into an average that obeys the TDP constraints. Intel's works similarly, but we're not talking about that today. An example from an AMD document says this, quote, when instantaneous power exceeds TDP, the processor returns to max power within 10 milliseconds and further converges to TDP within 30 milliseconds. The long-term power consumption of the processor, computed using an exponential moving average accumulator, will not exceed TDP. The potential to consume max power exists, but only in exceptional circumstances when power management is disabled. End quote. This is the same argument that Intel makes. Just because you see short-term power consumption spiking beyond TDP does not mean that TDP has been broken. Verifying the truth of that argument is up to reviewers. Clearly, and this has been done for a long time, but it's revisited every generation. So to be clear, using Intel as a counterpart, we're really not focusing on them today. This is going to be a really long video already. But you have something like a 90-95 watt TDP, the CPU will sit at that TDP in power consumption, despite all the disclaimers we made earlier. And it'll do that only with 1, MCE disabled, which is exiting spec, and 2, turbo durations expired. Once you're under turbo, that number will jump over 100, you might be 120, 130 watts, something like that. Next up, finally, AMD says this in its document. Conversely, if the smart algorithms governing Precision Boost 2 detects thermal or electrical conditions beneath these peak values, quote, headroom, it should be well understood by now that the CPU's boost algorithm is free to convert such headroom into higher average frequencies. Okay, so that's it for AMD's official explanation. The big takeaway here is that it's entirely possible for AMD to pick a TDP value it wants first and work backwards from there to get that to derive that value from a formula by plugging in numbers it wants. If you disagree with that statement and you think we're being overly critical by calling this a free-form formula that doesn't have many concrete numbers, then we'll read you this AMD Reddit statement. The quote says, notice also that this formula allows you to poke things around. A lower theta CA, better cooler, allows for a higher optimal CPU temperature. And further, in response to our own questions, AMD's representative mentioned that, quote, as you would expect, the higher end models assume a superior junction temperature stemming from a better thermal solution. Again, the TDP number is chosen by the CPU manufacturers. In this instance of AMD's formula, on which we are focusing today, it can be used to work backwards into the other numbers, depending on what number was initially desired. None of the numbers used to calculate TDP are direct measurements of the heat the CPU puts out. The closest one is TCase, which is AMD's recommended maximum temperature for getting rated performance, not a measure of heat output, to be very clear there. AMD is telling the truth when they say that TDP has nothing to do with power consumption. Anyone can tell that the 3950X is going to draw more power than the 3800X, that it's going to produce more heat than the 3800X. Its die layout is different, so of course it will. The 3800X, the 3900X, the 3950X, all of those are 105 watt TDP parts, but they don't produce the same power or heat when operating under stock conditions. So it's completely possible if AMD recommends the same TCase temperature, the same T ambient temperature, and the same cooler quality for all three CPUs, then by definition, TDP is the same because of how the formula works. Our best guess for why AMD has even bothered to list a TDP that's obviously not really useful to your cooler selection, by its own admission, mind you, is that it justifies the use of the stock cooler for all three of those chips. And aside from usefulness in marketing and proxy internet commenter wars that many people will fall prey to and battle with each other over, is Intel's TDP low or AMD's, when really the discussion should be, what's the power consumption like? And by the way, separate topic, the idea of trying to measure the temperature of two different companies' processors, which measure their temperatures in different ways in different spots and do different things, is extremely flawed. Instead of trying to measure temperature between A versus I, you should be measuring power consumption, because that's basically the temperature. That's all that matters with these things. So there's some efficiency loss. Yes, if you're going to post actually in the comments below, there's some efficiency loss through things like the socket, but all of that power going into the CPU functionally becomes heat. Whether or not it goes into the heatsink or some of it is spread through the board, through the copper and fiberglass layers and the pins, it's all going to be heat. So anyway, proxy internet commenter wars aside, we spoke to three major CPU cooler manufacturers about AMD's TDP definition as well. We've spoken with them about Intel's in the past. Enough with one company here today. The nature of the responses we received being that none of them will be officially on record because we are protecting, we don't want to identify the companies that said these things, but these are major players in the cooler market. They have combined experience totaling decades of working on CPU coolers, and all three of the ones we spoke to are engineering focused. They are not rebranding machines. They actually make things. When a new chip is announced, AMD sends a detailed document to the cooler designers called a thermal design guide. We have several of these we've obtained through sources in the industry. We're not going to put them on the screen because we don't frankly know what sort of typos AMD hides in there to identify leakers, so we're not going to put up a document without at least remaking it. But these guides contain all the information about power consumption and temperature. They contain a lot of information about voltages. They're extremely helpful. AMD does a great job at putting them together. They'd probably help a lot if you're designing a cooler. But TDP is not, by what the cooler manufacturers tell us, a number which is useful for designing the coolers. It's all the other numbers they get, not TDP. Specifically, that one is useless. So anyway, let's get into this. And by the way, I should say that's thermal design power, the thing that it's supposed to be useful for. Anyway, we're talking AMD here, but NVIDIA and Intel send out really similar documents. So everyone's got the same problems with every company when they're a cooler manufacturer. So this only covers the AMD spec for the CPU, and accounting for breaking spec with overclocking or harsh environments is up to the cooler company. AMD doesn't provide that information. That's fine. Companies test their own coolers using their own testing criteria. We have videos touring some of the various cooler companies in the industry. These are not necessarily the companies we spoke to for this video, but we've toured some companies that make coolers in the past, and you can see how they define TDP. And then a lot of them don't even put a TDP number on the box anymore. A company like Be Quiet will do it, but that number's different from what both Intel and AMD produce. In fact, some of the companies that we spoke with, when we asked if TDP is not a useful number, how should a customer determine which cooler is appropriate for their processor? And unfortunately, the answer from one of the companies was you should check reviews, which we're thrilled about that, but it'd be better if there were some first-party way to tell. Another company noted that it has scrapped its TDP numbers entirely in the past couple of generations because of how useless these numbers are, and instead has created a new database on its website where you can look for the cooler listed versus the heatsink recommended. A few of them have done this, so you're not going to be able to identify who that was, but that's the way they're recommending going about choosing a cooler. Specifically, buying based on a CPU, because the companies have to test these internally now. There's not a simple one-off number they can put on a box and have you walk away with the right cooler. Typically, these companies will produce a TDP ability internally used by pushing an amount of power through a dummy heater or a TTV, a thermal test vehicle, and then looking at the power consumption pushed into the TTV or the dummy heater and the amount of power successfully, or the amount of heat, I should say, successfully dissipated by the cooler. So the end metric that's being looked at is going to be the ability to constantly keep that TTV at a certain heat level, where that heat level or that temperature is the optimal operating temperature for the processor to achieve its performance. So this is done differently from AMD's on-paper calculation. It's done with thermal chambers, and the numbers are not the same. So it's impossible from a glance to tell whether a 200-watt TDP cooler means this is suitable for CPUs that AMD has designated 200 watts, or we tested this ourselves and it can dissipate 200 watts of actual power input reliably. None of the companies that make coolers whom we spoke with had a positive view of TDP. The responses range from polite recommendations to rely on third-party test data or first-party cooler recommendations on their websites to absolute discontent over what the companies see as misleading from both Intel and AMD. So that's not particularly encouraging. One issue is transparency. AMD is very open about its formula used to calculate TDP. That's cool. Why the number is used at all and why certain numbers are picked for certain processors is a little more vague, and values like T-ambient, T-case for each CPU weren't readily available until this content for all of the CPUs anyway. Theta CA isn't listed on the cooler boxes, so that's also minimally helpful. In conclusion, TDP is an overly reductive number, and it's only becoming more difficult to define with features like AMD's Precision Boost 2 that make every individual processor perform differently in different situations. Not just the SKUs, but the actual individual units. So the safe assumption is that any TDP rating, whether it's from AMD or Intel, is just an easy to swallow marketing device that looks good on a box. When buying a cooler, it's a far better idea to check the cooler manufacturer's website for specific recommendations. Many have moved away from listing TDP entirely in favor of detailed CPU cooler compatibility lists. Most importantly, never try to compare AMD and Intel TDPs against each other. They're different things, and they're defined in different ways, and both companies can tweak their values to make company A's processor look better than company I's processor. So what you should do is look for first-party data from the cooler manufacturers. They might over-recommend a little bit, but you can trust that it's been tested if it's on the list. Look for information from people like us or other reviewers. Not every cooler is tested, unfortunately, but that's the nature of it. And further, don't look for all caps forum posts about how processor X with TDP Y is better than processor Z with TDP. I've run out of letters. You get the idea. So it's not even advisable to make concrete comparisons between AMD CPUs using TDP, AMD to AMD. That's not useful either. Read a review, pick a CPU, check the website of a reputable cooler manufacturer for recommendations, compare different reviews against each other. Don't come to one source for everything. We'd obviously like that, but we'd prefer that you go to multiple sources to figure out what suits your needs. So that's the answer to what is TDP as AMD defines it, and how should you pick a cooler. Hopefully that ends a lot of questions, because we've seen a lot of misinformation, and Patrick's searching of forum threads where, because of the nature of Reddit, all you have to do is post a bunch of big words and reply really fast to the comment. You'll pick up a lot of upvotes, but then spread a ton of misinformation. And we did see a bunch of that, mostly relating to comparing TDPs between companies and comparing TDP within the same company as a metric of power consumption, which it isn't. But anyway, the best thing you can do is look at the power consumed by the chip and look at reviews of coolers. Thanks for watching. If you'd like to support this type of long-form, feature-focused content, we've been trying to produce more of this lately. Patrick does a fantastic job at doing a lot of the research on it. I'll do some of the research for some of the pieces as well. I'm more focused on a lot of the testing and test guidance, but these are big efforts. This one took about 3 weeks to do all the research, fact check it with a few people, get peer review privately with other reviewers, and publish. So you can support this content by going to store.gamersnexus.net. We have functional products. If you're not a shirt person, then you can pick up something like a mod mat, which is, we've got a 4x2 option and freedom units. We have a smaller option, about half the size. If you'd like that for GPU teardowns, we have toolkits for GPU disassembly that are completely custom made and very high quality by my spec. And you can also pick up shirts, or go to patreon.com/gamersnexus. Thank you for supporting this type of content. We really enjoy doing long-form stuff and hope to do more of it as we continue to secure your support. I'll see you all next time.